Stanford Science Seminar, Dr. Haomiao Jiang presents the avatar pipeline of Roblox. So he's a Roblox researcher, a scientist, a product manager, and he presents in this seminar how Roblox deals with three-dimensional avatars. In other words, you take a picture of yourself, you create an avatar, and fundamentally the main problem is the 2D to 3D transformation. That, according to Haomiao, is still the biggest problem. I want to discuss a couple of things. First, I want to give a little bit of history. I often go back to sort of the academic tree of the people that present, particularly in these industry seminars. It's really interesting to see where these people come from and also how they evolved, and it tells you a little bit about the company also that hires them and gives them important positions. So in this case, Haomiao's PhD was with Brian Wandell at Stanford, and he developed a simulation pipeline for co-design of sensors and image processing algorithms. So if you want to understand how image systems work, let's say the human eye or a camera, you have two fundamental components here. You have three fundamental components. You have nature, so you have something that you're seeing. Then you have the actual vision system, so the camera or the retina and the eye and the brain, in the case of the human, that absorbs the information. And then you have a processing pipeline. You have, whether it's a human or a camera, there's some sort of algorithm that translates wavelengths, light photons, into a representation of reality, right? So when we see a tree, we see a tree, and we all know what that means. And if we don't want to use English, we can use another language, but we all have a sense for what a tree is. I think, I could drop you in the Amazon jungle or in the middle of Shanghai or London, and you would be able to explain to another human being what a tree is. Actually, you would even be able to explain to animals what a tree is in some sense. So there's a certain representation of that. So there's these three components, and Haomiao's PhD was to work on the processing pipeline, on the algorithms, so there could be more simulation and co-design of sensors and imaging systems, and also a sort of a learned representation of computational photography. I'm going to dissect that a little bit more, but fundamentally, whenever simulation comes into play, it's because you want to generate more training data. That's what simulation is there for. And if you take, let's say, computation, you have just a limited amount of data, like even ImageNet or whatever image data set you have right now. It's fairly limited in a sense that you have ImageNet was, think about it this way, ImageNet was created for classification, but what 2D to 3D, for example, is trying to solve is not classification anymore. It's much, much more complex. It's understand a three-dimensional representation of an object, the lighting, the shading, the curvature, the nonlinearity, what's behind the object, the symmetry. So lots more things. And there's data sets for that, of course. But how about if we had simulation that we can simulate how, let's say, gradual shade translates. How do we perceive that? What is our pipeline? What's the kind of transformation matrix from what comes in and what we actually perceive in the brain? Or the same thing for a camera. What is the transformation matrix from light in and image out? And now if we take this into virtual space or the metaverse, as Haomiao says, then we have a three-dimensional or even four-dimensional representation, meaning you have also the time component. So Haomiao's PhD thesis is working on computational and simulation methods. And Brian Wandell, who is his PhD advisor, is incredibly focused on that. Almost in every seminar, he's a professor for neuroscience and imaging and computer vision, so he covers those three because he works on things like MRI imaging, computational imaging, and just generally is interested in vision systems, and he's always asking about sensors. So you can solve this problem like the three components again. There's nature, there's physics, right? We want to understand how photons work and whatever their nature is. We want to understand the sensors, and we want to understand the processing pipeline. And Brian is incredibly focused on the sensors. So you could have depth sensors, you could have LiDAR, you could have sensors that can have a lot more sensitivity in pixels, but just developing them and not changing the pipeline, the processing pipeline, would be sort of using a Ferrari engine without the proper tires, for example, or whatever the analogy would be. So you want to co-design, and for that you need simulation, and that was the PhD thesis about 8 years ago. So today, Haomiao is working on at Roblox. He's in this avatar group, and the goal here is really to take two-dimensional images and turn them into 3 dimensions. And the problem has been, to some extent, tackled, certainly not solved. According to him, that is still the biggest problem to be solved, how to turn 2D into 3D. And I think that's interesting also from a robotics perspective, because if we had 3D, if we had a good 2D to 3D representation, and we could add physics to that, we would actually have sort of a pretty good vision-based ground truth for a robot than to go and act in nature. This is not even on podcast. It's October 9, 2024. This is Krim Delco for today. The fund is down 1.4%. The market is up 75 basis points for the year. We are up 21.1. The market's up 21.1. We are actually relative to the market flat for the year. So we have the exact same performance, which is the first time this year that we have the exact same performance. So this seminar that I'm talking about here is a SIGN seminar. So it talks about mainly computational photography, computer vision, and applications of computer vision to basically reality representation. And what I found so fascinating about this problem is, I think computer vision has been the foundation of AI. The AI revolution started with ImageNet, and it was all about classification. Now today we're much, much further ahead than that, of course. We're 12 years into ImageNet, and we're certainly not talking about classification problems anymore. I think those are solved. Segment everything has been able to, in a unsupervised way, pretty much classify anything you want to classify. So classification has been solved. One of the bigger problems now is 2D to 3D, and I think this is a very important problem for the metaverse, for Roblox, which is kind of a metaverse company, but it's also a big problem for robotics, and that's why we're so interested. And that's why we're actually doing this presentation here for people that are wondering why we're talking about this. Just as a short recap, here at the Orange Capital Partners, at the Not Even On podcast, we talk a lot about knowledge creation. We talk a lot about how we work, what we do. And we're generally in the knowledge creation business. The purpose of Orange Capital Partners, the hedge fund that we run, is to generate wealth by investing in fundamentally new concepts and engineering practices. For that, we obviously need to understand what's going on in science, and we see ourselves sort of in the sweet spot between science, technology, and entrepreneurship. So when scientific concepts get transferred into technology and are ready for entrepreneurs to be picked up and turned into businesses. So having said that, we see computer vision, of course, and robotics as the big frontier. Please go back to some of our most recent episodes where we talk about our positioning and the reason why we are investing our capital in particularly in real-world AI. But having said that, we think that 2D to 3D transformation is one of the key problems, actually, that still hasn't been solved in robotics properly. And that's what we're trying to tackle here, and that's where Haomiao's presentation actually comes in. So the problem of 3D representation in general, so if you just sort of step back for a second and look at the problem in a systematic way, we have three components here. We have nature, we have the image processing sensors, and we have the algorithms that turn whatever nature gives us and feeds the sensors, and then processes something that we consider as a representation of reality. So that's what image processing kind of means in a more dissected way. So let's go step by step. And this is the first part of this episode where I'm sort of talking about Haomiao's PhD thesis and Brian Wandell's work and how important it is to dissect these three components and then tackle certain problems from the perspective, let's say, of nature, i.e. physics, or image processing systems, i.e. sensors, or the processing algorithms. So let's talk about the nature. This is the one I'm not going to spend too much time here. That's basically physics, optics. How does light propagate from the sun to Earth, and then how do materials reflect light? Because that's what we see. Okay, so let's just remind ourselves what it means to see. It means to actually absorb the light that is not absorbed by the object. So when we see a green tree, that means the tree does not absorb the green wavelength. So the tree actually is not green. The tree is anything but green. That's one of the sort of paradoxes of our vernacular, which is we call nature green. If you're an environmentalist, you're green. Well, in fact, nature is not green. The Amazon jungle has absorbs all the photons except the ones with the wavelength of green. But that's okay. That's just sort of as a side note. The point here being is that there's obviously a lot to be studied in physics also. How do materials reflect light? How does high temperature, low temperature change the light reflection? How does geometry affect light? How does water, humidity, I don't know, things along those lines. Now, that's not the part of this episode. That's certainly not part of Haomiao's PhD thesis, so I'm not going to discuss much more, but I just want to say we have physics, right? Let's not forget that, particularly now that AI is getting Nobel Prizes in physics. Maybe it's worth reminding that physics itself is also still a science, and there's a lot of knowledge to be gained in terms of physics. And we could also, just as a tangent here, ask ourselves, okay, at what granularity actually are we visualizing things? For example, once we go down to the atom or subatom or nano. I just attended a presentation yesterday by a physicist from Colombia who works on shining light on nanoparticles and then creating what's called something, I think it's called polaritron or something like that, which was actually a model developed by John Hopfield, the Nobel Prize winner in physics, yesterday announced. And he basically found a theoretical model to explain how light interacts with nanoparticles. And what happens then is that you have this combination of light and the particle. So it's not just that light reflects a nanoparticle, it turns into a new particle. Back to this presentation, this was just a tangent. So we have nature, right? What Wandell and Haomiao work in the PhD thesis from 2016 is they work on the processing algorithms. So once you have nature that transmits light, so photons with a certain frequency, wavelength, transmits it to a capturing device, let's say the human retina. There is certain technology in the human retina, and that's the sensor. And then there's the processing pipeline. So there's an algorithm that takes that information and turns it into a symbolic representation. So something that we call reality, something that we call a tree, a bicycle, a swimming pool, a sky, a sun. Whatever we see, we give these things names. but the names are, of course, just symbols. But more importantly, also, there's a certain meaning behind it. There's a certain phenomenology behind it, something that gives us a sense for what a tree feels like and smells like and all of those things. So all of these things happen in our brain, and it's part of the actual processing pipeline. So now, when it comes to digital imaging systems, there's this idea of the co-design of hardware and the processing pipeline. And why is this idea so powerful? Well, because we can have very advanced sensors. For example, sensors that can have depth information, sensors that can have directional information, like light field cameras. We have maybe stereo cameras that can computationally develop depth. But if those sensors are not used properly with the proper processing pipelines, then you're kind of losing, power. You're losing efficiency. The other way around, you can say the same thing. Let's say you could have a much better. You could develop a certain algorithm for image processing, and then co-develop a sensor that takes full advantage of this particular algorithm. So this co-design idea is very powerful in my opinion, and most importantly also, it helps in generating virtual sensor systems, virtual imaging systems. So once we have a certain idea, and this is the core of Haomiao's PhD thesis, of how light is transferred into a symbol, or how it's processed, once you have a model for that, once you have a formal model, you can then use that to simulate all kinds of different perceptions. You could have a tree with different types of light. You could have shades. You could have humidity in the air. All of these things could be simulated, and then sensor systems could be built around that simulated data, and you could have synthetic data also then used for learning mechanisms. So when then the system is in the wild, it can very quickly and efficiently use AI or Gen AI to develop to represent what it sees and help whatever the problem is that it's solving, whether it's a robotics problem or an avatar problem or something along those lines. So that's the core idea here. I just wanted to discuss this because, again, it's interesting to go back and follow the academic tree of people. I think it helps understand where they come from. It helps also calibrate the problem that they're working on. And sometimes, not always, but sometimes it also helps understand the company. And in this case, Roblox, of course, is in the metaverse business, so it makes sense that somebody like Haomiao works there. Now, let's talk about the presentation, actually, of today, where he spoke about the pipeline of avatar creation. So the idea is that you take a two-dimensional picture, so an image of yourself, and then you create an avatar that is either looks the same or looks like something else. Those are two different types of problems. Now, Roblox is working on the something else type of problem. In other words, what they're interested in is that you want to play games as yourself, as your own avatar. They kind of have features of your face, of your body, but doesn't look like you. Let's say Meta works on the exact opposite problem, which is they want to have a photorealistic avatar, because what they want to do is use, let's say, an avatar for meetings or conversations with friends, things like that. So now the main problem is 2D to 3D. And there's a paper that Stanford produced in 2022. It's a paper with a couple of authors, Gordon Wettstein's on it and others. What's interesting about the paper is they present a generative adversarial network, a GAN, that can transform 2D into 3D. Now that's 2022. I believe today probably we will be looking at some some hybrid combination of transformer, maybe still GAN, maybe some even convolutional neural net or something like something a little bit more, you know, a bit more, how should I say, a bit more contemporary. I don't know what the latest 2D to 3D architectures are. What's interesting here is that there is the problem per se, I think, is what interests us the most. It's pretty obvious that lots of people are working on it, and we might expect some pretty advanced solutions. But the problem is, look, if you take a two-dimensional picture, you don't know exactly how the three-dimensional picture should look based on just a two-dimensional image, right? So you need some learning. You need some, maybe you can use a foundation model. You can use NeRFs. NeRFs have been very successful, which is, NeRFs is the idea that you use sort of linear radiance fields and sort of extrapolate from there how things should look around the edges and behind and on the side, and how nonlinearities and shades and light and all of these things work from the two-dimensional image. Now, again, this I just mentioned NeRFs. So you have a different image processing pipeline, and that also requires different types of sensors. So there we are again with the co-design question. What I want to discuss here, just to finish the episode, I mean, this is something we could talk, we could have seminars about this. But the interesting thing is the application for robotics, because we've been talking about this before. Kai-Ming He, for example, works on, basically visualizing physics. And I think this is the first steps. Visualizing physics, which means understanding physics from vision alone, which is a holy grail. We're pretty far away from that, but to me, that's the most interesting problem in vision, and also one of the most interesting problems in robotics. Because once we understand physics, we can then build much better robots, semantic robots that don't just walk around and act like robots, but actually have this human-like understanding that water is different than an egg, and an egg is different than a tree and a stone, and so on and so forth. So we're pretty far away from that right now, so we're not going to get excited about this. But fundamentally, what we want to say here is that understanding 3D from 2D is a big, important step towards a better robotics pipeline. Now, to some extent, that is already taking place. For example, we have depth estimation with stereo cameras. That's already a pretty big deal. And actually, Brian Wandell mentioned this in the he asked that question: how does 2D to 3D sort of work with these new types of sensors and new types of technologies, computational photography technologies, and things along those lines. And there's some interesting aspects. So I think, to summarize, I just want to say that this co-design idea, I guess this is the key message that I want to take away from this seminar, which is the co-design idea between the three components, which is nature, i.e. physics, sensor technology, and image processing pipelines. This co-design idea, I think, should be furthered. It should be more studied in depth. And I think the problem should be tackled like that. I guess that's the key. The problem should be tackled from a three-dimensional perspective, from physics, sensor, and image processing. And there's certainly also huge advances in foundation models, which could help, which is basically this sort of multi-dimensional representation of reality that then could be sort of used in a predictive, autoregressive way, and have good approximation, good predictions of how, let's say, a 2D to 3D transformation should work. Thank you.